direct and indirect band gap. Welcome to Decreation's resources. So try to visualize energy band diagram where you are plotting E versus K, energy versus K. Now we now know that energy gap is basically between the conduction band lowest level and valence band highest level. So imagine that you are plotting energy with respect to wave vector or propagation constant k. So it's E versus k, so it's also called EK diagram. Now if it is a direct band gap semiconductor, the valence band maxima, that is we can call it EV, and conduction band minima, we can call it EC, they will exist at same value of k. That means if you want to excite an electron from valence band to conduction band, it just needs to absorb a photon of energy which is equal to the difference between EC, which is the conduction band energy, minus EV, which is the valence band energy. So the band gap energy EG is equal to EC minus EV. Now photon, as we know, it's a particle of high energy and low momentum. So the electronic transition in the direct bandgap semiconductor is almost vertical when you are thinking of an EK diagram, because it's occurring, the maxima and minima occurred at the same value of K. Now in the reverse process, excited electron will fall back to its ground state, and that time a photon of energy Eg will be emitted. The excitation of electron to conduction due to photon absorption is called carrier generation, and the reverse process, that is the falling back of an excited electron to valence band ground state, that is called carrier recombination. Now let us consider the case of indirect band gap semiconductor. Here if you visualize its EK diagram, the conduction band minima does not exist exactly below the valence band maxima. So since now here K axis is representing electron momentum, excitation of an electron from valence band to conduction band will not only require a photon absorption, but another particle, namely phonon, also needs to be absorbed. Because if it absorbs only photon, it will go in vertical straight line. But here the two values are at different values of K. So in order to go there, you need to have a phonon absorption as well. Now phonon is a particle of low energy and it has high momentum, and we know that it's related to lattice vibration. So phonon absorption is required from the point of view of conservation of momentum. So to repeat, in indirect semiconductors, instead of one particle, that is photon, there are two particles involved, namely photon and phonon, so that the generation and recombination of electrons take place. And so the probability of generation and recombination is less in case of indirect bandgap semiconductors. Now you might wonder that which of these are used for solar cell applications. Well, both are used, both direct and indirect bandgap semiconductors. Now out of the semiconductors that you know, silicon, the simplest one, it's an indirect bandgap semiconductor. And if you think of compound semiconductors like gallium arsenide, cadmium telluride, or cadmium sulfide, these are direct bandgap semiconductors. Now, as we noted that in indirect bandgap material, both photon and phonon are required to excite an electron from valence to conduction band, and that the probability of light absorption is less. So one requires a thicker layer of indirect bandgap semiconductor to absorb complete solar spectrum as compared to the direct bandgap semiconductor. So in terms of magnitude, the thickness of silicon solar cell could be 200 micrometer, while that for solar cells made from say gallium arsenide or CDT, that is around 1 micrometer to 3 micrometer thickness. So you can note that the thickness is much larger in case of indirect bandgap semiconductor, namely silicon.